But roughly, we just break up using rectangles. Rectangle is the easiest idea. So we assume that this is the x direction, t direction, and we break up in the x direction like using delta x. Right? It's possible to unevenly divide, but then it's too difficult to program, right? So we evenly divide the given domain using delta x, and similarly using delta t, and there is some relation between delta t and delta x for CFL condition for the guarantee of convergence. So we will cover this kind of thing later. The first thing is breaking up. Because we broke up the domain, we want to know the value at specific point. Of course, our goal is solving differential equation, meaning we want to know the solution or height at any point, right? We want to know the height at this point, we want to know the height at this point, and so on, right? But here, we cannot find the height at every place. We want to limit our focus on the grid points, right? So we want to find height here, we want to find height here, we want to find height here, right? So we want to find height at grid points instead of every point. Of course, if you need height at this kind of point, then the only way is either breaking up more or later approximating this value using surrounding numbers. So there are two ways of doing it. Using surrounding numbers, you can take the average or weight average, or you can break up more. In any case, we know the height at these things because we want to know the height at these points. We label the position. For instance, you can call this U11 or U10. You can call this U20, or you can call this U21, right? So you can call any way you want, right? You break up and then you label them. Of course, if you label them unevenly or not uniformly, then you will have trouble when you program, right? So there is no reason to name these things strangely, right? So we just try some reasonable idea. We use reasonable idea to name these things. In any case, we name those unknowns, and this is the second step, right? In other words, we now have many unknowns, right? We have this unknown, or sometimes something is boundary and known, right? But sometimes, for instance, this unknown. So we have many unknowns. For instance, we have 100 unknowns. Those unknowns represent the solution, right? Solution at specific points. Then how can we find those unknowns? We need to solve some equations. In other words, we need to generate equations of these unknowns, right? We need to generate equations of these unknowns. Then we can somehow find the solution. For instance, U31 minus U21 over this direction representing delta x, right? Equals, for instance, U22 minus U21 over delta, something like this, right? In any case, the detail is not important. The idea part is important. So we have many unknowns, then we generate the relation of these unknowns or equations of these unknowns. It's not just one. We have many relations at individual rectangle, right? Inside this individual rectangle, we generate this kind of relation, right? We generate this kind of relation. So we generate enough relations like this, and then by solving this system, we can find these unknowns, meaning we solve the differential. So this is the idea part we covered last time. And if you have a question up to this point, ask me, because today we will handle advanced ideas of this finite difference method. Any questions? Then, roughly, how to convert is the question. So there are three things we need to consider. First thing is how to convert. We have a differential equation for every point in the domain, right? For every point in this domain, right? So this differential equation is valid for every point in this domain, right? For every t and x in this domain, or x and t in this domain, depending on the order you chose, you can write it tx or x, doesn't matter, right? So depending, we have a differential equation which is valid in every point of this domain, but now, instead of this thing, we need to create a relation. For instance, let's pick generic position, say x, I here, and then t, k position, right? Or x, I will use j. So t, k, and xj position, or t and xj, doesn't matter. Any index you can choose. So I want to find the matching relation to this one. Then, roughly, if you forward the differences, the derivative with respect to t is like this. U of x, I will use this order. I will write it this order, right? So I will write it in this order from this point on. So u of t, k, u of tk plus delta t, and then u of tk delta t u of xj minus u of tk xj divided by delta t can replace this u of t, u sub t. Any questions? It's obvious, right? This is the direction, the t-directional derivative, right? T-directional partial derivative. And similarly, the right-hand side can be rewritten this way. U of t k xj plus delta x minus u of tk xj over delta x, right? So we can write the equation this way. But as you can see, it's very tough to write the equation this way. We don't like this notation because once we break up the domain, t sub k, t x sub j are all fixed, right? These are all fixed. So we don't have any reason to call this way. So we just call these things using simpler notation. We call this u k plus 1 j, right? We call this one u k j, and then we call this one u k j plus 1. We call this u k j, right? So we can rewrite the relation using this simple notation after defining the unknown values, right? After labeling unknowns, right? After labeling unknowns. So up to this point we covered last time, and if you have a question up to this point, ask it. Then I will rewrite the differential equation on the third column here. So this differential equation became u k plus 1j minus u kj over delta t, and then u kj plus 1 minus u kj delta x, right? But even this is too much. Assume that we have many variables, or we need a lot of stuff. So like about a few weeks, I considered the possible notation. Say I went to someone's lecture, and then notation is very important, I heard. In fact, I also felt the same way, because the differential equation is simple, but the expression here is not simple. So I will introduce notation. So I saw the table of Greek letters, and I felt gamma is a nice better, so I chose gamma. So I will use gamma notation this way. So for instance, we have many variables, right? So we have many variables. For instance, something, and then something here. And assume that I have forward here, f here. This means forward the difference in this coordinate. And then this means what? If we apply this operator to u, this means u of first variable, and then forward difference means, for instance, if this is x2 variable plus h or delta t, delta x or anything, right? So I will use h, and then this thing minus u of x2 variable, and then over h. You follow me or not? So from this point on, when I have this kind of situation, I will use just gamma of this thing, right? Gamma of this thing. Second variable is called x variable, right? The first variable is x1, second variable is x2, third variable is x3. So I decide to use this notation, and similarly we can define backward notation. So I will change the location. For instance, assume that I have back and then this thing. Then what does this mean? I am intentionally writing different situation. Then you will see the point. It is x1 variable, and then second unknown, and then u x1 minus k over this one, backward difference. Do you follow me or not? So I am just defining forward the difference and backward difference by using just gamma at appropriate coordinates, right? First entry or second entry or third entry. First variable, second variable, third variable. Then suddenly I can rewrite this thing very simple way. Oh, it is first variable forward difference, right? Second variable untouched. I decide to use just that, untouched. Second variable untouched. And here, first variable untouched. Second variable forward. Then, as you can see, once you master the mechanical part, like the routine part, it is very clear, right? It is very clear what we are doing. Do you follow me or not? In other words, we can convert the differential equation directly to this kind of thing. Just operator relation, right? If you can just apply this operator to u to get the relation. I will slow down. I want all of you to understand this side. Of course, do not write these things outside this class because I'm just developing these things. So nobody uses it. So if you completely understand this thing, then I will introduce about 2 more cases and then fully explore the method people have developed until now. Not everything, but important method people developed until now. So, take a look. You can write the differential equation this way. You can write the differential equation this way by using this operator. First thing forwarded, second thing untouched. First variable untouched, second variable forwarded, right? And people call this kind of method upwind method. Of course, later I will give you summarized version. But right now, just giving you the idea with the notation. Then what else might be necessary? We need about 2 more things necessary in this direction. Gamma of C. Gamma of C will be defined. Gamma of C will be defined. Gamma of C means what? Gamma of C applied to U is what? U of x first variable plus h minus U of x first variable minus h. It is central, right? Central differences. What is the distance between these 2 points? 2h, right? The distance between 2 points. So I have forward difference, backward difference, and then central difference. Forward means distance h away. Backward means distance h away. Central means 2 distance away. So we are almost ready. And one more thing that I want to define is the grid advancing grid. For instance, assume that we want to consider, for instance, forward difference, backward difference, central difference in this direction, then there is no problem. So we have step, for instance, n, right? But I'll assume that we want to consider the same thing at the next step. In other words, I want to consider this thing at the next step or previous step. Do you follow me or not? So we want to consider some kind of thing in the next step or previous step. Then how can you use it? So what I decided to use was plus or minus. For instance, if I say plus, this means we are considering this thing in the next step of this coordinate. Do you follow me? So I will go to the next page and then write. Save this and then open. So this is the thing. U of n plus 1 j minus u of n j is called, by my notation, what? F forward u, right? Do you follow me or not? I forwarded, so I consider the forward difference, right? Forward difference in the first coordinate. So why do we care about this notation? Because today I went through at least 10 different methods. I do not write down the equation, long equation, without giving you much idea, but if I use notation, then you will see what is going on. This is the reason why I introduced the notation. Now, I want to consider this thing. Everything is the same. Everything is the same but second coordinate. So everything is the same. Up to this point, same. But here, instead of j, I want to have j plus 1. Then how can I represent this thing using the notation? And I chose a lot of things and then decided to use plus here. In other words, second coordinate is advanced, right? It steps forward, right? Second coordinate. So do you follow me? This F means this difference. This F means difference. This plus means advancing these things. So if you don't understand, ask me if you. Do you completely understand this idea or not? Then to check whether you understand this thing, I'll ask you to write down the result of this thing. I use backward u. What is this? You may use n and j. With n and j, with index n and j, please write this thing. What is this then? Right? You understand it or not? Now you want to either advance or step back, right? How? For instance, what is this? What is this? So it's kind of plus or minus only changes the level, right? Instead of considering this level, considering the upper column or below column or right side, upper row or below row or right hand side column or left hand side. Roughly, these are the steps. And if you have a question, ask me. If you don't, then I will begin to introduce tons of methods people have developed. Oh, right. Sorry. Yeah, it is divided by delta. Assume that this is t direction, right? First one is t direction. It is, yeah, you are right. I'm writing down delta t. So this delta t step does not change, right? We once divided, even if you go up to the above row, the delta t amount does not change, right? So roughly, these are the cases that we will use. And if you don't have a question, then I will introduce tons of methods using the simple notation. First of all, of course, knowing the essence is more important. Assume that u to the use of t equals use of x is the differential equation. Then some people decide to use this direction. For the first derivative, so I will specify the order of the variables. T variable first, and then x, right? U means u of t and x. So this is the case people develop, and this is called upwind method. Do you follow me? Is this all? No. People, yes? It is operator. It is operator. So you assume that you pick v function, right? You assume that you pick v function. Then this operator works on this v function to create these kind of things. Assume that you have specific functions such as u, then u is used. Assume that you use v function here, then v is used. Assume that you use h function, then h is used. Good question. So we are handling operator level, just not the specific function level operator. Forward, backward. F is not a function. F is forward. So I use I decide to use three letters: forward, backward, and center. It's very intuitive, right? The forward, the difference. F means forward, the difference, right? E means backward difference. T means center difference. Right. So yeah, first variable, second variable change, right? This time is first variable change. This means second variable change. If nothing happens, I use stop. So you will see the advantage of this thing. Right now, you need some kind of learning curve. We should overcome this kind of learning curve. But after this is done, then it will be very intuitive. So no questions about upwind method. Then I will introduce tons of methods developed by many people for a long period of time. Euler method. Euler method is this way. Of course, it cannot be very different from the above one, right? But now you have some choice. Instead of using F, what would you use? Euler decided to use what? C. This is Euler's method. Of course, to practice these things, please write down this thing when you use u function. In other words, when you apply this thing on u function, what is the relation? Please find it. Apply this on u function, right? Then what is this thing? Please write in full equation form. Then you will see the advantages and why these things help you. Because if you write like 10 terms in the equation, you don't see the picture. You don't know what is going on. But if you write this way, then you see the picture. Oh, essentially, the same thing, but instead of handling forward difference, we are handling central difference. So if you finish writing down this relation, let me know what your result is. Of course, you may choose any index of your choice, right? Any index is okay, but I decided to use this one. So did you get these things or not? If you didn't get, then check whether you have difficulty in the notation. So I just translated this thing by applying this operator relation to u. So differential equation becomes operator equation. Of course, you are learning about this operator gradually, and later, when someone asks you about Upwind method, you don't have to write down this kind of thing, or Euler method write down this kind of thing. You just say, oh, this means Euler's method. Why is it so advantageous? Because we will cover like 10 or 20 cases today. Then do you want to memorize these kind of things, or just memorize this thing or understand this thing? This is the reason. So I will assume that everybody understands these things, and I will continue. Because of Euler's method, someone consider a different thing, because you need to write papers, right? Edward Euler is developed. So there is some saying, oh, publish or perish. So people continue publishing stuff. Someone used forward but left behind backward, then great chance. What do you think is the direction? You get it? What is the direction? Hey. So you are geniuses. People spend a lot of time to develop these things, but you now just get it. After seeing this, oh, people are ready to forward and backwards. Do I have any room? Oh, fortunately, at this time, you were born too late. Fortunately, people at that time found an empty spot. What do you think he said? You're a genius. Did you already take the course before? This is it, right? So once we learn the notation, suddenly you don't have to write down millions of different formulas, or you should memorize different case by case. Oh, no. You just write it in this way. So essentially, all these are same, right? What is the difference? You use forward, right? And then forward, center, backward, center. This is it. And even second order, I will define squared and then use the same thing to develop different methods. Roughly, you got the idea, right? So if this is used, then it's called upwind method. If this is used, it's called Euler's method. This is used, then backward Euler's method. This is used, then leapfrog method. I will show you. This backward means here, only change happens here. Because this is forward, assume that we change this to backward. I will use, assume that we change this to backward. Then what changes? This changes, right? This change happens. Only this. Right. So forward, backward, central, depending on these things, sometimes called Euler, backward Euler, leapfrog. So I wanted to write down these stuffs on the web for a long time, but I didn't know what notation may help that. I'm still developing. So about the end of the spring break, I may write something on the web. Put something on the web. And if you don't have a question, then I will continue. If you have a question, because these are straightforward ones, but now the straightforward ones are taken. What should we do? We should tweak to publish, right? Tweak. I will show you how people tweak. So do you have any idea? Let's do it. So I will show you the case. Euler looks nice. So, I will take on this Euler stuff and then tweak. So you assume that you are a researcher needing to publish a paper to stay in the job or do something, right? Assume that you are a researcher needing some kind of breakthrough. Frank Nicholson decided to tweak this. They focused on second term. Yeah, second term should be tweaked out. Decided to use average, right? Average. What average? Whatever. I want that two term. Then one term could be this. And we learned about some kind of operator advancing. What is your idea? Do you have any idea? Right, a little bit different with an Euler method. Advance. Let's advance. Instead of just considering 3 points, one row up, right? One row up, consider one row up, then average. This is called Frank-Nicholson method. So quick done. Quick done. So this is the idea of developing stuff. And if you can tweak with different ideas, then you may check whether those things are already published somewhere or not. If nothing was published, then you can publish yours. So please check up to this point and ask me. Or if you want a conversion of these things to equality form, then ask me. Then I will convert these things to equality form. But it will not be beautiful. I will show you the equality. So people could not sometimes understand the idea because everything is written in this form. Then you are somehow swamped with many stuff and then confused. But if you write it this way, then it is very clear, right? You know, you get the point. Oh, they average the current and the next level. Yes. Of course, we just write down the Frank-Nicholson in old school form, right? In some school form. And it looks like this. U n plus 1 j minus u n j over delta t equals 1/2 times u n plus 1 j plus 1 minus u n j j plus 1 minus un j minus 1 over 2 delta x plus un plus 1 j plus 1 minus un plus 1 j minus 1 over 2 delta x. Assume that you somehow learned Frank-Nicolson method and then study this thing and then try to memorize this thing for a long time. You might not feel comfortable about the method later, right? But if you just use this operator, then it's pretty good, right? It's average. So I will pause and then you can check whether these operators helped you or hurt you. Because you don't understand what is going on. So please let me know. I want to know whether you prefer this kind of direction or the other direction. This is my draft. I'm still typing it, and then I will go to the result like this. And later, I will let you know how people tweaked further. But this might be enough. So I will go to the next equation. Oh, I see. I will use stencil version too. So I will show you stencil version. But this is helpful because you can directly convert these things to equation. The stencil version is good to understand what kind of terms are involved. So if I stencil version, it looks like this. Here, forward means this, right? This one and forward means this thing, and then this thing means upward, right? So these two things determine this thing. So these two things determine this thing. This is the stencil, and if I write the stencil, then it looks like this. Right? This is the stencil of this piece, right? Yeah, I'm just I'm sketching it and then checking whether you follow me or not. So do you completely follow me up to this point? If you don't, then let me know. So I showed you Upwind, Euler, and then backward Euler, and leapfrog, and then if you completely follow, I will write the stencil of this Frank-Nicolson case. I wrote down the differential equation. I converted the differential equation into finite difference equations using notation, operators, and I showed you stencil. In other words, to calculate this value, we need to know these values, right? Then the second thing that I want to mention is this one. Some of you might find this very strange because how do we know this upper level why we don't know this thing, right? That is legitimate question, right? That's a legitimate question, and that kind of thing will be mentioned after giving you the idea about the generation of these kind of equalities, right? So any questions up to this point or not? Because if you have a question, ask me, because you just snowball. You just suddenly become very, very complicated. So if you have any questions, ask. Then the differential equation of this pattern. Differential equation of this pattern. As you can see, we see second derivative, but our forward, central, backward difference do not handle second derivative. So I will introduce c squared term. So c squared term will be introduced. So gamma, and then some variable, and then c squared term and stuff are defined this way. U of these stuffs, and then some variable x here, right? It's not fixed number, just say x. Somehow this variable x plus h, and so, right? Minus u of 2 times u of x, and then following terms, and then finally u of something, and then x minus h, and then this, over h squared. So I will call this c squared operator, right? C squared operator. It's obvious, right? Central operator squared, right? Second order difference. X minus h, right? X plus h, x minus x. So x plus h, x minus. I have taught this method over 5 years, and each time I hated writing this kind of thing. But I didn't have any idea to develop any operator. I still developed this. Nobody knows that I will be successful. But in any case, with this, we can write the method. So first of all, Euler method. Euler method is this one. Forward in the t direction, right? And then you fix the first variable, center plane. So when you have second order derivative, usually c squared is used because we don't forward twice, right? We don't forward. Any questions? Now, backward Euler. So, do you have any idea about backward Euler? What is your idea? What is it? Back, right? I will give another name. People sometimes call this. Sometimes call this method forward difference method. So people attach different names to the same method sometimes, right? Sometimes people call this forward difference method and call this backward difference method. And it's nothing but Euler's method. But you don't have to worry. You can just rely on this operator expression, right? You get the clear picture about the operator. I will sketch the stencil very soon. But if you have any questions up to this point, ask. Then I will sketch the stencil. It looks like this. Right? Then let's develop second order Crank-Nicolson method consider the case, right? Frank-Nicholson method for this case. So can you write down? So what is the left-hand side? Gamma f dot, right? Gamma f dot is the left-hand side. The right-hand side is rewriting these things, right? Averaging these things. How? We write this thing at least. Right? Euler method, or 4 different methods, and then we advance, right? We advance 1 unit. This is called the second Crank-Nicholson method, right? I will pause, and then you can check whether you completely understand up to this point or not. If you have any doubts, ask me, because once it begins to snowball, how can you say? Very difficult. Then leapfrog. Leapfrog. You might know already the answer, right? You might know the answer already. Euler, what should we change here? Only one letter should be changed here. What? This F should be replaced by what? T, right? The leapfrog method is T. I'm explaining all these things using the operator, right? Operator expression. And I will pause, and then you can check wherever. I will sketch the pencil too. Oh, sorry. Sorry. I was confused between, I was copying top portion and then somehow copied the Crank-Nicholson. Thank you. Later I will let you know anomaly handling. There are some anomalies in some cases. How to handle anomaly will be mentioned after explaining the relation finding. Because relation finding might be an easy step, right? So I will cover these things, and then I will let you know how to handle anomalies, such as how to handle these kind of things. You may not know these points and how to handle these iteration stuff. How to handle this kind of thing. Assume that in this first step, and how to handle this. Let's not worry about anomalies or difficult things. Just focus on the idea of conversion, or development of this kind of method. As you can see, how many methods did I mention using operators? Without using operators, we might cover about 3 or 4 methods. But with operators, I explained a lot of things, and then I will introduce more. Then let's consider Laplace equation. Laplace equation, or sometimes we can change the right-hand side to create the Poisson equation, but we don't want to worry about the right-hand side. Right? It's not very difficult to handle general f instead of 0. As soon as you have this thing, then it's very trivial. People do not even spend any more time on this, because other than this, what choice do we have? You follow me? As you can see, the derivative is converted by gamma, right? Derivative becomes gamma. And then second derivative becomes c squared, right? The gamma of forward, backward, central becomes first derivative, right? First derivative has gamma, forward, backward, central. Second derivative becomes gamma, c squared. You need any explanation or examples? Then wave equation. So I'm just oozing, right? I don't have to worry about writing down any expression. Just oozing. You may already have the idea, right? Just equality here instead of equality. Already more than 10, right? Other than anomaly handling, you can handle, take a look, advection equation, heat equation, and Laplace equation and wave equation. Roughly, these are the things you see. Then what about higher order dimensions? Don't worry, no big trouble. I will handle higher order equations. Especially, you see the advantage of this notation in higher order equations. Assume that you have this case and write down the relation using general formula, then it will be very long and you may be lost while you are following the ideas, right? But now, using the notation, you can write it. You follow me? I wrote down one case. Please write down two more cases. This is Euler style, right? Please write down backward and leapfrog style. Please write down backward or leapfrog style of this method. Third. You like dot or zero? I was a little bit worried about using dot or what do you prefer, zero? But if I use zero, the font is bigger, and then if I write zero too many times, it takes up too much. I decide to stop. You prefer dot? You see this? No, no, no. It's the choice. If I decide to use dot, then dot is used. If I decide to use zero, then zero is used. What do you prefer? Did I use zero? Dot. Zero means dot there, right? But I somehow, when I somehow wrote zero, because we have no definition of zero, so zero means dot, but yeah, I had hard time determining the letter or choice. First of all, I looked at many letters, but this gamma letter has empty space, right? That's the reason I decided to. Any questions about this thing? Now, backward means what? This is backward difference, right? The same thing, right? And then leapfrog means what? Central, right? Now, this is 1 plus 2-dimensional problem, right? It doesn't matter 1 plus 2 or 1 plus 3 or 1 plus 4. But I will start at 1 plus 3. Is it very hard or not? Just add one more term. Because I don't use many letters, I'm even considering removing this comma. This comma takes up space, right? So F dot dot dot. I will decide it later. matter what is given, you can use these things, and you can change these changes to backwards or center, leapfrog, right? You focus on the differential equation conversion instead of writing down too many terms if you use operator. So roughly, heat equation is done. Heat equation for 1 plus 1 dimension, heat equation for 1 plus 2 dimension, heat equation for 1 plus 3 dimension, all done. If you have a question, ask me. Of course, if you have enough time, you can develop Frank-Nicholson method for this thing, right? Frank-Nicholson method for this thing by advancing using average, right? You can develop anything. Nobody developed it before, right? And if your thing may have a little bit better result than this, the result before. Roughly, this is it for 1 plus 2, 1 plus 3 dimension, unless you have a question. And now the Laplace equation for 3 dimension. In some sense, it is not even nice to write these things because it's so obvious. About this time, you know what the answer is, even if I don't write anything. You already get the picture, right? What is it? I have habit of writing 0, sorry. 0 means dot, but later I will decide whether I will use 0 or dot. If you think this is better, something is better than the other, you can email me during the break, because about the end of the break I will post the receipt and send a paper to the journal. Any questions? In some sense, it's very boring, right? Because it's so obvious. Now the wave equation. 1 plus 1 dimensional wave equation is done. So 1 plus 2 dimensional wave equation. Do I have to even write down these things? Or I just, you get the picture. Essentially, where did I write 0? Right after erasing it, writing. One plus 3 dimensions. 1 plus 4 dimensions, 5 dimensions, no matter what, you can handle it. I didn't write 0. But in my opinion, all of you completely understand the idea, right? And if someone asks you to write the equation, even though it may take a long time, you may be able to write the equation, right? A lot of indices, four indices here, right? Then what else people develop? In some sense, I completely covered all the equations you may encounter in this numerical analysis course, essentially. Heat equation, 1 plus 1 dimension, 1 plus 2 dimension, 1 plus 3 dimension, right? Wave equation, 1 plus 1, 1 plus 1 plus 3. Laplace equation with 2 variables or 3 variables. Everything covered, right? A Vector equation, ut, ux. Right? then how can you twink or write paper? So I will just show you one case, but there are tons of cases, and I will check whether I can convert every cases to operator or not. If it's successful, I will write a paper and send it to the journal. In other words, completely you can convert stuff to operators that everybody can easily understand. But if I fail at some cases, then I will reconsider or develop further. Let's write the case. This is called box method. And box method essentially is like this. So assume that we are converting this thing. We are converting this thing, then box method converts this way. Oh, F forward, and then F forward plus average, right? You follow me? Usually, we use gamma F or gamma something. It means derivative, right? So we take two derivatives, so it's the average. And then, average of the right-hand side. Then, if we take right tensor, it's like this, right? Do you follow me? Or forward creates this thing, right? And then advance, right? We advance, then it creates this. So do you now know the reason why this method is called box method? So this kind of tweaking is possible, right? So people tweak while using later, not now, but later I will introduce using like 1/6, 5/6 weight or 1/12 weight. A lot of different ways are used because this means derivative, right? So derivative average, then it's derivative, right? Derivative added and average, then it's derivative. There is no back, all forward. All forward. So take a look. I will write it, then you will see. If I write box method using formula, you will really feel the advantage of using operator. I will write the formula. I will cancel out one half, right? One half is canceled out. Then, use of n plus 1 j minus use of nj over delta t. This is the first term. And the second term is use of n plus 1, j plus 1, minus use of n plus 1, use of n, j plus 1, over delta. Why? Why does this happen? Please indicate the reason. Just one letter. Please indicate the reason why we get j plus 1 here. Plus, right? Plus. Now the right-hand side. So assume that you learned these steps using this notation, then box method might be a nightmare, right? Because you need to know all these terms without any mistake, right? But people sometimes make mistakes. This is it. This is the box method. So do you prefer operator expression or this expression? Especially, when I write the box method on the second order, 1 plus 1 field equation, you will see the advantage in English and the screen area. The box, right? So take a look. we want to determine this thing. This thing is unknown, right? The x marked one is unknown. Or others are used, or others support this thing. In other words, you solve the equality, this equation for this term, right? Move all these terms to the right hand side. You solve the equation for this. But this appears at one more place, right here, right? We select these things and then move all other terms to the right. Some books did not produce this thing, but gave the final result. The final result is way harder to understand than this thing. I will write for you, then you will see the reason. So I will call delta t over delta x. Say, what kind of letter might be good? Lambda. I will use lambda. People use lambda to represent this notation. And it looks like this. I multiply both sides by delta t, then we get this thing. You follow me or not? So I collected this. But problem is this. We have pairs. This one and this one are paired together. And this one and this one are paired together. This one and this one are paired together. And this one and this one are paired together, right? Then it will become very complicated. So I'll then other problem may happen. Even if we get advantage, we may get disadvantage. So I write down this term on the left-hand side, right? So I handle the two terms. I will track down the terms that I handled. This term and this term I handled with lambda, right? And then the next term is UNJ term. UNJ term is handled. This becomes plus UNJ term minus lambda. I will track down the used terms. The next term is this one. Then plus, I will handle this term first. Minus UNJ plus 1. Then with this, if it moves to the right hand side, it becomes plus 1. And then here, UNJ plus 1 plus lambda. And then finally, before going into this, I will track down the used terms. And finally, one used here, right? UN plus 1, J plus 1. And this is used on the right hand side. And then I completely wrote down the formula. Then divide both sides by 1 plus lambda. Divide both sides by 1 plus lambda. So some books who did not even mention about the idea or stuff, just provided the final result that I will write upstairs. I will write it downstairs instead of upstairs because if I write down downstairs, upstairs, then I will go back to text system. This is right. Assume that you somehow saw this thing. Do you really have any clue why it is called box method or how people develop this kind of method? Just you look at the formula and memorize. But someone asks us about box method, you don't have any confidence. Right? Oh, there is a complicated formula. Instead of providing this kind of formula, I decided to provide the operator relation. So as you can see, even though it is a little bit tweaked, it is a little bit tweaked version, this is very intuitive, right? This is very intuitive. Like derivative is converted this way using average with forward twice, right? Forward twice average, right? And forward twice average. This way, it is very reasonable, and we know why it is called a box method. But here, we lost all the ideas right behind. Just we have formula, but somehow you make mistake. You cannot you cannot find the reason, right? That's formula. So if I subtract u sub n plus 1 and j plus 1 from both sides, then I will get minus 1 times this, right? Mm-hmm. Yeah, anomaly handling will cover that kind of thing. So after covering relation part, I will let you know how to really do it using the iteration we do. Then final thing, and then we'll take a break. People developed this thing, and for the heat equation, people apply this thing, and this is what I briefly mentioned. I will not provide you with this kind of formula in this case. I will just provide you with this kind of idea or operator part. If you want further, you can solve this on your own. So this is box method. 5/6 of operator forward direction, right? And then 5/50 is not enough, right? So 1/12 more of this operator. And then this one. And then the right hand side is year stretch, right? People were desperate, right? People were desperate to publish papers. So I just give you the idea, right? Roughly, what people did was this thing. You follow me? So the left-hand side of the derivative is separated to three parts. 5/6 of, right? 5/6 of forward difference, and then 1/12 of forward difference with advanced, right? Advanced row, right? And then, right, back row, right? And then 1/2 of central difference, and then advanced. So these kind of people develop a lot of it. So let's take a break until 3:05. And we are almost completed. We are almost completed this case, right? How to find the relation part was almost covered, and then I will summarize. I will summarize this part one more time, and then mention about anomaly handling. So before going any further, let's consider the tensor here. Because of this, what points are required? Because of this, what points are required? this and this 2 points. Do you follow me? Because of this point and this point are required. Because of this, what points are required? We advance to the right-hand side, right? Because of this, we advance to the right-hand side. These two are required. Because of this, what is required? These are required. Do you follow me or not? And then because of this, what is required? And then because of this, what is required? Okay? So we have all the usage of this box, right? Box is bigger than one-dimensional box. But in any case, I showed you how people develop stuffs. And in fact, in many cases, people use just one or two nice cases, like Frank-Nicholson case. Of course, you are not required to use all these cases. Just use anything that you prefer. Use any method that you prefer. In other words, I showed you, for instance, 5 different methods for advanced equation. Then pick anything and then use it, like upwind method. So I do not want to return back to this part anymore after this time. So if you have a question about this relation determination, ask me. Then let's go to the anomaly handling case. So there are reasons for anomalies. For instance, gamma c squared requires, right? Assume that you have a function, gamma c. Then gamma c requires this kind of thing, right? So the second derivative of f, right, requires these things. Then this is the situation. Assume that we want to find the second derivative at this point. How can you define the second derivative at this point? This is the anomaly, right? This is the anomaly. We want to find the second derivative in this direction. Why? To find the second derivative at this point, we should have the information like this. But this is the leftmost point, right? So we don't have this thing. So we should handle anomalies like this, especially in the wave equation, by using repeated finite difference notation. So let's return back to finite difference notation. Finite difference notation says if A, B, C in general position, then we can say A, B, C, and then generally this is the same as second derivative of this function at some point with that, right? Generally, if we have n plus 1 numbers here, then it is nth derivative with n factorial. Here, you don't prove this thing, but you use it. Some number between the interval. So we have interval of ABC, right? Some number located somewhere here, right? I use psi, right? So psi is inside this interval A and C, right? So this is the general theory, and we don't cover the proof of general theory. But now we want to consider the derivative like the above at the boundary point. If we chose the first point here and second point here, we wouldn't have any problem. But before going any further, let's write down the details of this. By definition, this is f of AB minus f of BC over A minus C. Right? And this is A minus C is like H and H, 2H away, right? And this thing is f of A minus f of B over 2 and H, right? H minus f of B times f of C over H, right? If I write it, then it becomes f of A minus 2f of B plus f of C over H and H squared, right? This is the case. So if we equate these things, we can write the second derivative. We can write the second derivative by f of A 2 times f of B plus f of C and then H squared. This is the reason why second derivative converted this way. 2H comes from this place, right? And the 2H comes with. But now when you have repeated roots, this changes. If you don't follow me, ask me. Because once you understand this thing, the repeated root handling isn't very difficult. No questions? Then, now what I will do is this thing. Oh, assume that we don't have A, right? In other words, A is the same as B, right? So we don't have A. In other words, B is the beginning point instead of second point, right? In the previous case, then suddenly, here everything changes, right? Everything, especially, we cannot write this expression because this is 0, right? Because this is 0, we can write this expression. F of A and F of B are the same. But in finite difference, f of AA is not 0. F of AA is defined by this thing. In finite difference notation, f bracket AA is f prime of A, not 0. Because both H, this H goes to 0 and this goes, both numerator and denominator goes. We cannot use H either downstairs, right? 0 over 0 type, right? 0. So we should use this. Then everything settles. So let's write it. If we have this situation, f of B, B, C, because A is equal to B, 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 C, then what happens to this one? This is equal to f of f prime of A, I replace it, f prime of A, f prime of B, sorry, prime of, I will follow the same way so that you can later study. So instead of skipping any step, I will write down everything. So I wrote down this thing, and by this definition should be equal to, or this theorem should be equal to second derivative at some point, and then 2 factorial, right? But now if I write it, then this becomes f of B minus f of BC over B minus C. Any questions? Just writing the same definition. And then f of BB equals f prime of B, right? F of BC is f of BC. And then B minus C is minus H. B minus C is minus H. I somehow wrote down plus and plus H, but in fact it should have been minus H here, and a minus H. But eventually we get to H. Not a big deal. But I'm just correcting the calculation. If you have any questions up to this point, ask me. Then let's finish it. not a good idea to use minus h downstairs, so I will use plus h downstairs. Because I use plus h downstairs, I should write it this way, right? EC minus f prime of b. Right? I did plus and minus. Wrote it this way. And then now it's time to write it this way. F of b can be rewritten. I will write c first, f of c minus f of b. Then I can write h, right, instead of minus h. Do you know what I mean? Instead of writing b and c with minus h, I wrote down c and b and then with h. And I have prime of b. And h. Then what happens if I select these terms? Then f of c minus f of b over h squared. Minus f prime of b over h. So done. Essentially done. In the wave equation, we need this kind. Why? I will show you. But before going to wave, because here I use one variable function, but in the wave equation, we have time variable and spatial variable, right? So we have at least two or more variables. So it will be more confusing than this thing, so you should understand this part. So I will write the differential equation one more time. UTT equals UXX is the one that you want to solve. Then, essentially the idea is this: C squared dot equals dot C squared, right? The problem is this. We are starting at the boundary condition given by the problem, right? So this boundary is given, or some sort of boundary is given, right? Either this is given or some sort of is given. So these kind of boundary conditions are given, and we know these points. So assume that we break this up into like explanation. I use a few lines. So take a look. All the boundaries are already known. But it's good to write these things using some notation. So I will say 0, 0 here. Now I say 1, 0 here. 2, 0 here. 3, 0 here. 4, 0 here. So all these are known. And in addition to this is known. 0, 1, 0, 2, because of the boundary condition. 0, 3. And then 4, 1, 4, 2, 4, 3. In this sense, these are just numbers. But when you use numbers here, it's difficult to program. Because of this reason, we just call this U, even though we know these values. You follow me? Then we should name these unknowns. So let's name these unknowns using different colors. We call this U11, U21, U31, U12, U13, U22, U32, rename this. Then let's take a look. I will use stencil. If we sketch the stencil, because of this C, we need these things. Do you follow me or not? Because of this vertical or time directional central differences, we need 3 points. Central differences require. Center difference equation requires 3 numbers in the stencil. And this direction requires 1, 2, 3, right? So we have this kind of stencil. In other words, to determine this thing, we should know this one and this one. So what is the problem? What row is the problem? Determination of what row is the problem? You see, or first row is the problem, right? Why? To determine this, we need these things. But we don't have this thing. So this is the anomaly, right? This is the anomaly, and we need to know how to handle this. So in wave equation handling, if you blindly apply any kind of method, you will definitely fail. Why? Because we don't have this thing. We don't have this. And you may say, oh, let's go down and then begin at this point. Then it will happen to the same thing will happen to this point, right? If we go down, the same thing. Always, the initial row will be the problem. The most important step in wave equation handling is the first row handling. But after somehow finding the numbers, then we don't have any anomaly. Assume that we have found the first row, right? Then afterwards, determining this means using the previous 2 points, right? Using the previous 2 points. No problem. So most important row is the first row in wave equation. So someone just blindly implement those stuff without considering first row and submit, the result will diverge or have strange effect. The major reason is the first row. Then I will let you know how to handle this first row. In this first row, we don't directly write this thing. We change this a little bit. So this part for the first row should be changed. The first row should use this kind of expression, and I will use this relation. I will use this relation here. It is like this. Oh, it is use of generally generic position here could be J, right? Could be J. Generic position here is J, and then this row position is 1. Right? And then I'm just converting this position using multidimensional use of 0 J. J is the generic position of delta. And then oh sorry, I made a mistake. I varied this thing. I fixed. Sorry for that. I labeled it this way, so I should follow my label. I should switch J and R, and then I will use N. N. 1 minus N0. Because I used 0 in the second position, right? I converted this thing, and if you have a question, ask me. Over delta t squared. And then the derivative is nothing but the partial derivative in the direction t, right? This represents the partial derivative of the function u in the direction t of the position, right? N0 is not actual input value, n0 is the index, right? So if we convert to this, then it's xn, and then 0 is equal times 0, it could be 0, right? Times 0, and then delta t. So I convert the left-hand side this way, and right-hand side is. So this is the difference. But what is the thing here? This thing is derivative was derivative over 2. This thing is derivative or derivative over 2. Is this thing derivative? Is this thing derivative or derivative over 2? Is this thing derivative or derivative over 2? Like this thing is derivative over 2, meaning the second derivative is what? The second derivative is 2 times fc minus ft over h squared minus f prime or t over h. Okay? Because the derivative over 2 is this one by definition. Okay? So this thing multiplied by 2 is the left hand side. Thank you. So I will slow down and you can check whether you completely follow this step or not. So only the first step should be handled because of anomaly, right? Because of anomaly, we manually handle it instead of automatic handling. But if you have a question about this thing, ask. Usually, a wave equation should have the boundary condition and the boundary condition with derivative, right? Two things should be given in wave equation. So this is given by the problem. This is given by the, you know this value all the time. You know this value all the time. And then you label these things, right? You label these things. If you don't have a question, I write down the full representation of this. Then, so this is only for the first row, right? For other rows, use just simple conversion. So this should be equal to the right-hand side, right? Right, delta x squared, and then u n plus 1, 0, 2 times u n 0 plus u n minus 1, 0. I wrote down the relation, and I will even provide you with the first row formula. Then I can multiply both sides by this. I will multiply both sides by this to simplify the relation. And the left hand side is un1 minus un0 minus delta t un ut xn t0. This is the left hand side. And the right hand side has this thing multiplied, and let's call this lambda, right? Where lambda equals delta t squared over 2 delta x squared. I will define lambda here for convenience. And then un plus 1, 0, un0, un minus 1, 0. And you can simplify these things to write it in this form, right? So un1 equals un0. un0 appears here and then here. 1 minus 2 lambda. And then lambda times un plus 1, 0 n minus 1 times 0, and then finally distance. Delta t u t x n t 0. I completely wrote down the formula of the first row. Then to practice this thing, please write down the formula of the row after the first row. In other words, second or third or generic row. Please write down the formula like this in generic row. In other words, we don't have any fixed row number, right? This is the first row. So please write down u and j plus 1. U and j plus. Distance variation. Please write down u and j plus 1 term. U sub n comma j plus 1 term, so that we can completely write down the formula for the wave equation using finite difference method. Somehow wrote down second instead of x. So you can correct this thing by rewriting. In other words, if you write t time variable first, then you very complicated, but it doesn't matter. So you get it? So we wrote down the equation of the first row using, instead of 0, I used j, right? J is equal to 0, then we wrote down the relation. If you have a question, ask. I replaced the 0 by j, right? J is equal to 0. Then please find the relation like this for other j than 0. So let's do it. Then completely wrote down the formula. And as you can see, for the first row, we have this kind of relation. But for other rows, we have different relations. Right? For the first row, we have this relation. For other rows, we have this relation. So take a look at the similarity and difference. We have this thing, but we have 2 times this thing, right? We have this thing, but now we have this thing. And we have this thing here, we have this thing. Essentially, wave equation is completely explained. Of course, somehow I use time variable second. It doesn't matter, right? When I read, I somehow labeled differently. So everything is, location has changed. But the great advantage is this one. My notation doesn't have any preference, right? It doesn't matter, right? So when I designed, I designed this way. When I designed somehow, I designed this way. I called it U00, and then I called it U10 instead of just saying U01. So I designed this way. So somehow 0 is second portion. And then time 0 line is here, right? Time equal to 0 line is here. So 0 becomes this time, right? The second variable becomes time instead of first variable that so there is no big difference. But when I designed it, I designed this way because of this reason. First and second row. So you will see this kind of problem when you solve problem. Unintentionally, you somehow change these things and then calculate different way. Your intention might be calculating in this order, but because of this kind of index handling, you might calculate this first and then that comes out. But in any case, there is no harm done because essentially we solve the problem even if we said xt instead of tx. Right? So in this sense, what I used was u xt function instead of tx function. So in this, if we just keep this thing, then this is okay. But if you want to reverse it, the only thing that you see, the only difference that you see is here. Right? We usually use this time variable first. I will pause and then you can check whether you completely follow these things or not. Yes? We don't iterate in wave equation. In this case, we don't iterate. It is one-time pass. Yes, in this case. Look at the stance. When you go up, all these are already known. But later, when you handle different anomalies, I will let you know. Yes, different type of. For this case, we don't have any. We don't have that anomaly. We have this missing row anomaly, right? Missing row anomaly. Yeah. It's just one time, one pass. So questions about wave equation? I completely explained it and handled the wave equation. And in fact, because generally when the differential equation is given, this function is also given. So you don't even see these things because t is fixed. You don't even see this kind of thing in real problems. You will see the initial derivative condition given by some function, right? Some function of x, right? So you will see some function of x. In reality, you don't see that in the computing system. This thing is given by the problem. So take a look. Even if we switch the order of variables, do you see any difference? Essentially the same, right? So you should, when you design, you should be extremely careful, as you saw, right? Once you switch it, then you should switch everything. And then you should find the correct order. Because when you do loop, especially double loop, your intention might be horizontal first. But in reality, you might do vertical. So you should be very careful. I saw, as I mentioned, every year I saw the answer doing vertical loop first. Then wave equation done, and finally I will cover Laplace equation, and then afterwards, about the Laplace equation time, I will let you know the iteration. Laplace equation handling is this. Assume that you have a rectangle, which is not a square. So assume that your domain looks like this. Then you can break up anyway. But the best way is using squares. You break up. Of course, sometimes it's impossible to break up using squares. You know what I mean? Somehow we have mismatch, then it's impossible to break up this way. But then try to use squares. If it's impossible, then the formula is a little bit complicated. In other words, try to make dx direction and then dy direction the same, right? Try to make these the same. You will have advantage. But if you don't, then break up and then use the formula. Then what happens is this one. uxx plus uyy equals 0 becomes gamma c squared operator and then dot, and then plus. By the way, using this notation, I mentioned 22 different methods of FDM. Without the notation, we might cover about 5 or 6 at max, right? But with the notation, we covered 22 cases of FDM relation. Any questions about this? Then this time, let's design it correctly. So we have this direction. Then first term should change, right? So here it is u0, 0. And here I should call this one u1, 0, right? Right? Isn't that correct? Why am I always confused? Why do I have a feeling that this should be u1, 0? Really not? This is the x direction. This is the y direction. The thing changes here, right? It changes here. Really? Yeah, my God. Last problem was different. I designed it this way. Because of this reason, I even changed the top stuff. But this time, if I want to get this directional derivative, right, this directional derivative, then I should use the difference of the first entry. I think this is correct. Last time, I didn't match my design to the equation. I reversed it. I just sketched something, and then I matched the equation to my design. That's the reason why T and X will change the index. But here, I don't think I made a mistake. But if you take this time, then so this is done, right? And then, similarly, U01, U02, I mean U1, always like this. U11, U21, U31, U41, and then U02, So I completely wrote down these things, and if you have a question, ask me. Then, after designing it, we should write central differences. So because I used the same delta t and delta x, we can call delta x and delta t h. Then u, the generic position, I assume that you have u like I, j, or j, k. I will call this generic position j, k, right? Generic position j, k, then j plus 1, k minus 2 times u, j, and then k, and then plus u, j minus 1, k. Do you follow me? This is the directional derivative, right? This directional derivative. And then the other one, h squared u, j, k plus 1, minus 2 times u, j, k, and then u, j, k minus 1 equals 0. Then, can you solve this for ujk? There are ujk appearing, and then h and cancel out. We intentionally did it. But as soon as we can cancel out, then some factor lambda is multiplied. Right? The only difference is lambda difference. It's not a big deal, even if we cannot match. And ujk equals 1/4 times uj plus 1k, uj minus 1k, plus ujk plus 1, and ujk minus I. And then if I sketch the stencil, it looks like this. Diamond shape, right? So by using surrounding 4 points, you get the middle point. But if you have a question, ask me. Oh, thank you, minus. So after this, you can determine it using, by averaging these surrounding 4 points. The problem is this. Initially, we know these things. Initially, we know these things. But we don't know these terms. So what if we want to find this value? What if we want to find this value? We cannot. Right? We cannot find this value. You follow me? We need surrounding points, but we don't know other values. We cannot find. Because of this reason, anomaly handling of this case is this. Oh, let's fill these things with something in the first place. Instead of just filling this with 0, we just fill this with reasonable things. So, for instance, assume that you decide to use row, then assume that this number is like 5, and this number is like 10, right? This number is 5 and 10. Then we use a line from this to this. Then 5, and then next guess might be what? This guess might be what? 6, and then 7, and then 8, and then 9. Even though these are not actual values, we feel anyway, right? We feel anyway using this kind of line, or vertical line. Any line is okay. Horizontal line or vertical line. Any line is okay. And assume that you may pick a number. What number do you like? Here, one number. You pick your own number. What number do you like? What number do you like here? Then you fill these things with appropriate number like this one. So roughly, we have the distance 3 and then 5 units, right? So 3/5 might be good, right? And then here, 6/5 might be good. And then 9/5 might fit. And then 12/5 might fit. And then this is 15/5. So we fill those numbers, fill those unknowns anyway in the first place. Why? Because we need surrounding. So anomaly handling of this kind of elliptic equation or Laplace equation provided. So we fill those unknowns with something in the first place, and then after filling these things, now we calculate this value using these initial values, right? So this is it. I saw solutions a lot of times, and some people just fill these things with 0 and got useless results. Fill these things with reasonably close things, and then iterate these things. So what is the step? I will behave like a computer here. We initially calculate this thing, right? We calculate this thing. We calculate this thing, and then calculate this thing, calculate this thing, calculate this thing by using surrounding points, right? So how do we calculate this thing? By using these 4 points, right? By using these 4 points, we calculate this thing, right? And then after calculating this thing, by using these 4 points, we calculate this thing. So we somehow calculate these things, and then go up, and then we calculate this thing, we calculate this thing, this thing, this thing, and so on. So we calculate these things one time. Well, is one time enough? No, because it's iteration. We need to calculate one more time. So we calculate this thing one more time, and then calculate this thing one more time, calculate this thing one more time, calculate this thing one more time, and calculate. Is 2 times enough? Is 2 times enough? No. These 2 times are not enough, so we need to calculate one more time. So let's calculate this thing, calculate this thing, calculate this thing, this thing. So we iterate many times, right? Are 3 times enough? No. We calculate this thing, we calculate this thing. So we calculate as many times as possible, or until we have this norm close to 0, norm of the matrix close to 0. So we calculate many times. It's called iteration, right? So we calculate these things, and then back, and then calculate these things, and then back. Right. Because they are zeros. Because you have bad thing in, bad thing in, bad thing out, right? Because you have bad thing in, then you cannot expect good things. What do you mean by? There is no guarantee. 0 sometimes is close to the solution, then there is no problem. But 0 could be far away from the solution. Then 0 is so dominant, you cannot overcome. So it happens. Right. Right. Yeah, that kind of thing can happen. Yeah, but I saw some fluctuating case. There is no guarantee. I saw some fluctuating case. So it's not a good idea to use zero because sometimes the zeros, if we assume all inner parts are zero, then even if we try very hard to overcome, we may not overcome. Then just we cannot reach the goal, just to stay in some limiting point below. So that really happens. So try not to use zero. You fill these things with some kind of linear thing or some reasonable thing. Right, that is reasonable. But sometimes some people just might be lazy and then decide not to do anything, just fill this with zero. Then suddenly he cannot reach the goal. He cannot reach the roof. It just goes up and down, up a little bit, and then the limit is somehow underneath, not the roof. Sometimes it reaches the roof, but sometimes it cannot reach the roof. Impossible. I saw that kind of thing. Usually norm might be a good idea, but norm is not the guarantee either, because if we reach some kind of thing, then the best thing might be just returning back to the differential equation part to check everything. But yeah, that one is also possible. That's the reason why, in the first place, fill this with nice things and then instead of zeros. Top row, you mean the lid? Everything is boundary is given. All these things are given by the problem. Yes, all these are given by the problem. Everything surrounding this thing is given in the elliptic equation. To reach, right. Not necessarily. Even that doesn't guarantee very much. Because of that reason, people develop different methods, multi-grid method, and black and white, all sorts of things. But the best way known now is just initial roof, right? We just use initial roof and then begin. Because once we begin with different stuff, then we don't even know. But once we begin nicely, then almost always we can get a reasonable answer. Not necessarily many iterations, but assume that we begin with like this kind of roof, reasonable roof. Then after a few iterations, we arrive. And then we can use, at that time, we can use norms or something. Or as you mentioned, center difference. Then I will assume that you completely understand this idea. Then finally, anomaly handling 3. We handled the 2 different anomalies. First anomaly was missing row anomaly, right? The second anomaly is this elliptic equation, right? Like without the inner numbers. Final thing is, assume that stencil looks like this. Assume the stencil looks like this. Then we have a problem. How do we know surrounding numbers while we don't know the number x, right? So that's a problem. So in this case, the final anomaly, usually it happens when you use backward difference, right? This is what you do. You use any possible forward method, right? You use, for instance, upwind method, right? Because all these are given. You use upwind method to determine this one, and you use upwind method or like Euler method or anything that works, right? So in other words, you use explicit method instead of implicit method. The explicit method is used to determine surrounding numbers. You follow me? So you initially fill the row with explicit number. Explicit method, right? So I will show you. Assume that you are solving this case. it stands like this, right? It stands like this. Then, initially, all boundaries are given. Then you fill these things with the explicit method, right? After filling this thing with explicit method, you iterate. You do iteration, right? So after filling this, you iterate. So you calculated this thing one more time using this stance, right? By using this one and this one and this one, you calculate this thing. Similarly, you calculate this thing using surrounding numbers and this thing. You calculate these numbers one time, and then return back. You calculate this twice. Are 2 times enough? No. 2 times is not enough. 2 times are not enough, so you should calculate one more time, right? You calculate as many times as possible, or you can use norm, right? Norm of this factor, right? You calculate this many times until it reaches some stable number, right? In other words, the norm between the previous calculation and the next calculation is big. Then you go to the next line. This is the handling of anomaly when we have steps requiring unknown values. So you use explicit method to calculate the first, like you use the rope or roof, right? In the elliptic case, right? You use the roof. Similarly, in this case, you should fill these rows, these entries with something, using some explicit method. And then after using explicit method and filling these things, you iterate. So in this sense, elliptic curve handling and this handling are similar. Elliptic curve handling, I mean elliptic equation handling, we handle this thing, and we used lines to fill the positions, right? Fill the values, right? This repeated heights. In this case, we fill these things with explicit method one time, right? We initialize these things one time. After the initialization by using explicit method, we iterate, determine nice row, and then after determining nice row, go advance. Then you may wonder why people use this kind. There is a major reason people use it. Major reason is this. Usually, explicit method is not stable. An explicit method is not very stable. But this kind of backward, right, method is very stable. People intentionally use backward method because it's stable. In other words, derivative calculated here isn't good for this calculation, right? Derivative calculated here is better, right? Derivative calculated here isn't good to determine this thing. Derivative calculated here is better. Roughly, this is the theory developed. Determine this thing. After filling this row, and we do the same thing, we calculate these stuffs, right? Using explicit, right? So we initialize this. We initialize this step. After initializing this thing using explicit method, we begin to iterate, right? We begin to iterate. So we recalculate this thing using surrounding terms. And then we need to do this kind of calculation many times, right? And then enough times. So backward difference method or this kind of implicit method has advantage. This is the reason I Crank-Nicholson method is so nice. Crank-Nicholson method. It uses 2 steps, the previous step and the current step. Then finally, of course, I will retype these things and then post the CFI condition. But without explanation, you don't understand the stuff. I will explain briefly and then write a few cases. So CFL condition, the first guy is a famous guy, like Courant. New York University has this institute, right? The CFL is the initial of 3 people named. These guys are, in some sense, very famous people. Theoretically, this is what they proved. The differential equation had dependence. In other words, to determine this position, generally xt, we need this kind of information, right? It has dependence, right? Domain of dependence. What did they say? They said this, numerical domain should include theoretical domain. This is what they said. He doesn't have us at all. Because what we want is clear thing or quantitative thing, not this kind of abstract. Okay? So this is what they said. The condition is this. When to have a solution, we need to have this kind of condition. So dependence, right? Mathematical dependence, the domain of dependence should be included in the domain of numerical domain, right? This is what they said, and then proved. But now, we are not very interested in this kind of theory part. We are interested in numbers. Assume that we are solving this kind of equation, advection equation. So general advection equation looks like this. Assume that we have C, U, X. Assume that we have this kind of advection equation. Then we use this kind of forward, and then step, and then this thing, and then something, right? So here, box is replaced by forward or backward or something. We are developing these kind of things. And when are these things stable? And let's write it in usual form that we can easily handle. Assume that we write it in this routine form. Then it looks like this. U times delta x un j plus 1 minus u n j. What is the name of this method? Name is what? This method is upwind method, right? Upwind method. Then what we have is this thing. Then let's call this lambda. They investigated lambda and then found the stability condition. And then for Euler's method, lambda should be less than or equal to 1. Euler method. And for instance, upwind method, the same condition. We should have this thing. Of course, there is a table I'm looking at, and then you will see this table. For leaf frog method, this number. Then one more condition is whether there is a guarantee or not. The second thing will be mentioned next time. But roughly, what does this mean? It means what? When you design, you should design the domain according to this theory. And according to this theory, how should you break up the domain? How should you break up the domain? You should break up this way. Assume that you have ut, which equals 5 ux, then 5 delta t over delta x should be less than 1, right? Then roughly this should happen. Roughly assume that these are similarly measured, then will this work or not? Will this work or not? In other words, if you use delta x about this quantity, delta t, and exact, will this work or not? Then delta t multiplied by 5 or delta x is greater than 1, as you can see, right? This domain will not work. You see the picture here? Then you need to have domain like this. Oh, this doesn't work, so you should have domain like this. You should divide further and then delta t, and then this ratio should be less than. If this doesn't work, then you should divide. In other words, people who took this course and people who didn't take this course may program similarly, but may not design similarly. Yeah. Because of some reason, I do not want to explain, because even if we do it, there are some things that we need to consider. Do we really have any restriction or stuff and that kind of thing, or we really have stable results or something like that? But I don't want to cover that kind of thing. I want to just post these things and then later explain each entry. So roughly this is it. And if you have a question, ask. Next time, after this brief review, I will begin to cover a finite element method in 2 dimensions. In 2 dimensions, we are handling finite element method. You already did 1-dimensional case, right? 1-dimensional case. We will handle 2-dimensional case. Then unexpected difficulty happens. The unexpected difficulty is the basis function. Basis function isn't just sharp function anymore. It is like pyramid, right? Not necessarily pyramid, but pyramid size, like tetrahedron or something, or harder stuff. So these kind of things we cover next. Let's start it.
I've got all these values going.